is if there were ever a time to do the algebra first, it's here. So when we start working on problems like you have a solid cylinder, you put it on a ramp and you let it roll down a vertical descent of 2 meters, how fast is it going to be going at the end? Don't put any of these numbers in first. I'm going to give you the numbers just to make extra work for the people who didn't listen to me. But you don't need them. Just do everything algebraically. The radius will cancel out, the mass will cancel out, and it'll be a nice simple answer in the end. So anyway, starting with linear or tangential kinetic energy formula, derive a formula for rotational kinetic energy. So the one I've just been calling kinetic energy all year, that I'm going to call Ke with a little subscript t. And you could either think of this as translational or tangential. Translation, hopefully you heard about that in geometry. Remember translations? Remember rotations? So they're rotations, yeah. Reflections, translations. A rotation is something's turning around. A reflection is something's being reflected. What's a translation? Just shifting like this. So you're not. So if I took this Ke with a little t there and put it over here, but didn't rotate it, that'd be a translation. So translational kinetic energy is kinetic energy something has just because it's moving along. What's the formula for that? Everybody knows it. 1/2 mv squared. So I want to take that and I want to turn it into the rotational version. And the first thing I want to do is substitute something for m. So what's the rotational version of m? I. But let me put it over here. I want to write I, and basically for a point of mass rotating around something, its moment of inertia is what? It's m what? R squared. So m would equal what? I over r squared. So I'm going to substitute this in right here. So this is going to be Ke rotational, and I'll leave the 1/2, but now I over r squared. And I've got to get rid of the linear or tangential speed or velocity. So over here, what would go on the other side of this that's the rotational version of this thing? The weird W? Speaking of the weird W, we were talking about omega, and somebody was asking, why don't we use the capital version of that? Because that's like unmistakably a capital omega. And somebody who knows what we will be using that for, tell me, what does this really get used for? This is ohms. This is great for ohms because it's an omega. So we don't want to use that for, you can use it for meditation, but don't use it for angular velocity. So anyway, is this true? V equals omega? Omega r. So instead of V right there, I'm going to put in omega r. So I have omega r squared, and I'll do a little bit more with it. 1/2 times I over r squared times omega squared, r squared. And what should I do with that to clean it up a little bit?
Cancel out the r squared.
Get rid of the r squareds. So we have Ke rotational equals 1/2 I omega squared, which is, kind of what you would have thought it would be. I is the rotational version of mass, and omega is the rotational version of velocity. And now we'll do the problem that was the warm-up, essentially. Calculate the final speed of a solid cylinder that rolls down a 2-meter high incline Cylinder starts from rest. It's got this mass. Got that. There are two red herrings there. The red herrings are, you're going to think you need to just like use those numbers for mass and radius, but you don't. Okay. I'm going to have to write really small. I'm going to draw a diagram too. You don't need to draw the diagram, but I'm just doing it because I'm a teacher. I'm trying to teach. So here we have the cylinder, and its height is 2 meters, and it's going to roll down here, and we want to figure out how fast it's going to be going when it gets to there. And a month ago, if I had given you this problem, how would you have solved it? Yeah, so conservation of energy. So we're still going to do that. In the beginning, what kind of energy does it have? Potential. And what's the formula for that? MGH. And I'm going to write it kind of small because, like I said, I know this is going to end up being tight. And then when it gets to the bottom, what kind of energy does it have? Kinetic. And if this were a frictionless box, what would the formula for kinetic energy be? 1/2 mv squared. And that's still the formula for part of the kinetic energy because this thing is translating, it's just moving. So the translational kinetic energy of this rolling thing is that. But it's also going to be spinning, so it's coffee. So, hey, I've got a question for you. So, two things. I always feel bad for people who cough. They never get bless you, so I decided to throw in a coffee just now. And then, right, is, yeah, it's okay. But the question was, I was thinking about this morning as I was brushing my teeth. Has anybody ever run across this in literature? The other class clearly doesn't read a whole lot. Has anybody ever seen that? So when I've read books about people who have hiccups, and this is how they spell it. But what I want to know is it spelled hiccup, or did they actually call it a hiccough? I know it looks like hiccough, but I've never ever heard anybody say hiccough. No, other people spell it with the UP. But I've also seen it like that. Nobody knows the answer?
What are you reading?
I don't know. I've read it a lot. You've seen it? Yeah. See, Max has seen it. All right. I need to finish. So there's coffee again. MGH equals 1/2 mv squared plus 1/2 I omega squared. These are the two kinds of kinetic energy that this thing has. So that is being apportioned out into the part that makes it go and then the part that makes it spin. And to resist any urge that you have to substitute this in for m, because the m's are going to go away. MGH equals 1/2 m by mv squared. And you could do this different ways, but the easiest way to do this is to make this compatible with these. We need to get m's and v's in here. So instead of I, what's the formula for the moment of inertia of a solid cylinder?
MR squared.
1/2 mr squared. You could look it up on the other sheet, but it's 1/2 mr squared. So now we've got an m here, and that's nice. And omega, these are all v's, so we need to get rid of the omega. So what do I substitute? What multiple of v do I put in here? Omega would equal v over r. Yeah. So if v equals omega r, then omega is v over r. So this is going to be v over r squared. And so I'm just going to make myself a little note here that v over r squared is v squared over r squared, right? Yep. So if this is really v squared over r squared, what can I do? I can get rid of the r's. So this r squared and that r, they can just kind of go away. What else can I cancel out? All the m's. Everything has an m in it on both sides. So you can divide both sides by m, get rid of all the m's. So I just got rid of all the m's and the r's, so you don't need the r or the m. And now let me clean it up. So this leaves us with gh on the left side equals 1/2 v squared plus what? 1/4 what? V squared. And that's gh equals how many v squared? 3/4 g squared. Did I say g squared? I meant to say v squared. So I'm going to skip a couple of steps. I'm going to multiply both sides by 4/3. So I'm multiplying both sides by 4, dividing both sides by 3, and then doing what else to both sides? Take the square root. So 4/3 gh, and the square root of all that gives me v. So if I want to know how fast this cylinder is going at the bottom of the hill, it doesn't matter what the radius of the cylinder is. It doesn't matter what the mass of the cylinder. Any solid cylinder of any mass, of any height, is going to get to the bottom of the hill at square root of 4/3 times 9.8 meters per second squared times 2 meters, 2 meters, which is 5.11 meters per second. I think it's cool.
Should I put this on the notebook?
What's that? I'm not putting it on there. You can memorize it, or you can derive it.
Okay.
So, but you could memorize. You could memorize basically this for every version of moment of inertia. Like, but why do it? Because you could just do these steps. Okay. So now we're going to do the same thing except for a hoop. Exact same thing. This isn't a disc anymore, it's a hoop. Is the hoop going to go faster or slower than the disc?
Slower.
Slower. Why?
Because it has a coefficient of 1.
What's the coefficient of 1? The moment of inertia, which means its mass is where? Its mass is way farther out. And I'm going to give it one more shot before I get up. I'll climb up there. No, I'm not. Angry dismount. Sorry, Miss Anthony. Or whoever's down there. Earlier, before I thought to use that tarp, I was just letting all the round objects roll onto the floor. That had to be really annoying for her.
Did she mention it?
No. The last time she had to come up here was they were taking a test, and we were dropping something heavy on the floor repeatedly. And she asked very nicely, "Could you maybe? We're taking a test." She was very nice about it. Okay, so good question. I didn't like it, I guess, or somebody didn't like it. So as I was saying, if you have more mass on the outside, which hoops do, then there's more inertia getting it going. It's going to go slower. So I'm going to write kind of what I did in the beginning, except I'm going to write the first step. You may want to skip it. So this is the amount of energy that the hoop has at the top. And this is the amount of translational kinetic energy that the hoop has at the bottom. And this is the amount of rotational kinetic energy that the hoop has at the bottom. And now all again, except in this second step, maybe I'll go a little faster than last time. So this needs to be 1/2 times I, which for a hoop is how many r squared? How many mr squared? 1. So this is 1/2 times just mr squared. And instead of writing what I did last time, I'm going to jump right in and I'm going to call omega squared v squared over r squared, because omega is v over r. If you square it, you get v squared over r squared. The r's cancel, all these m's cancel. So we have gh plus how many v squared this time? 1. So it's just gh equals v squared, so v equals the square root of gh. Now, do you remember? This would be, yeah, so this is a fun question. You remember when we were doing this with in just the energy unit, and we were talking about frictionless things, what would the speed of something be if you either let it slide frictionlessly to the end of this ramp or you let it drop directly down? Does anybody remember what that comes out to? If you drop something from a 2-meter height, when it gets to the ground, how many GH is it going? Yeah, so this would be V equals the square root of 2GH. So that's quite a bit faster than for the hoop. So the hoop is square root of 9.8, and in this case times 2 meters, and that comes out to 4.43 meters per second. And this next little thing, I don't know if it's important. Mr. Pennington liked this kind of thing when he was teaching. It says compare the speeds of thin hoops and solid cylinders in general after rolling down ramps. So what he did in his notes was he said, let's let this represent the speed of a solid cylinder after rolling down this ramp, or any ramp, and this represents the speed of a thin hoop. So if we divide them, if we do the velocity of a cylinder divided by the velocity of a hoop, after rolling down a ramp of height h, we get square root of 4/3 GH divided by the square root of GH, which equals what? What's the ratio there? What is root 4/3 GH divided by root GH? Yeah, it's just this, or 2 over root. I don't know. I don't know what the math teachers would want you to do. But basically, the velocity of the cylinder is the velocity of the hoop times 2 divided by square root of 3. So that'll always be the ratio of those. Doesn't matter how big the hoop is or how big the cylinder is. One could be tall, one could be short, one could be heavy, one could be light. As long as they're all rolling, they're always going to have that ratio of velocities at the bottom. Okay, so that is all you need, really. Well, that and some good common sense. It's all you need to do, or to do the homework. But we're going to jump on to the next thing, because tomorrow your homework is going to be on this next thing, and tomorrow's a short class, and we've got lots of time left. So now momentum. We've got linear momentum and angular momentum. Linear momentum, the symbol is what? We just did this unit. P. And the way you calculate P is m times v. So angular momentum, I have no idea why. I think when I get to this, I don't care anymore. But the symbol is capital L for angular momentum. Angular momentum, maybe.
Nope.
And instead of mv, guess what it is instead of m? It's I. Guess what it is instead of v? It's, lowercase omega. So there we go. So this is angular momentum. And there's a law of conservation of angular momentum that says, what happens to momentum? It stays the same. But there's kind of a rule. There's a little, I guess a caveat comes after. This is a requirement that comes first. So when, and here I'm going to cheat. It says do it in words. I'm not going to do it in words because I want to make a little visual riddle for you. So what does this mean? What would the words be that would say the same thing as this? Net torque. Yeah, when net torque equals 0, then angular momentum, or I'm going to write Li equals Lf. So initial angular momentum equals final angular momentum. And the equation, whoops, I think I just did it. Oops, dang, I jumped the gun. So that is the equation for angular momentum. And up here I was supposed to do it in words. I was supposed to say net angular momentum remains constant. Has anybody ever, well, one thing we'll do tomorrow is we'll watch people who are doing aerial skiing. Once they're in the air, their net angular momentum remains constant. And but they can speed up and slow down and do all kinds of twists by changing the angular momentum of parts of themselves. And you can also do this. I'm not like a dirt bike enthusiast, but if you're on a motorcycle and you're flying through the air and you want to, let's say this is your motorcycle and you're going this way. Oh, here I am trying to draw motorcycles again. That's not what it looks like. Okay. Anyway, if your motorcycle, if you feel like it's tilting down too much, you can make it start tilting back. How do you do that? Do you give it more throttle? Yeah. So why does giving it more throttle make the motorcycle go this way? Which wheel spins? This rear wheel right here is going to start going more clockwise. But if it goes more clockwise and the net momentum has to stay the same, then what has to happen to some other parts? They have to go the other way. So if you make one, like you increase the momentum of this part clockwise, that has to increase the momentum of the rest of the motorcycle counterclockwise to conserve the momentum. But anyway, this is what I meant to write up there in words. Write some other formulas for conservation of momentum. Maybe we'll do that sometime. That just can muddies the water right now. This was supposed to go here. Okay, ice skater. Before we do the ice skater thing, whoever's watching this is going to be bored for a while because I'm not going to put anybody in the video. Does anybody want to be the ice skater? This is where you get to spin around and go faster and slower. Somebody who likes to spin. Okay, come on up, Chris. Be the ice skater. And you've probably all seen this before, but that's okay. So what are we going to do here?
Give me some weights and spin.
Give me some weight. First, I'm not going to give you any weights. I'll just spin you. So how do you want to be when I first start spinning you? Arms out?
I don't know.
Okay. Doesn't matter. You want to keep them in? You want to keep them in? Okay, yep. I'm going to spin you.
Okay.
Whee. Now what do you do?
Oh, I twisted it. I shook.
Okay, put your arms out.
Put your arms in.
Oh boy.
Let's do it the weights. So hold the weights out as far as you can, and now pull them in. Put them back out. Okay, give me the weights for a second. Put your arms out. Do you think it's easier or harder for me to spin him now? It's when I give you these weights, put them out. If this force that I'm applying out here, I don't want to call it force. What do I want to call it? This is a spinning system. What do you apply to get a spinning system going? Torque. I'm applying a torque. At some radius to a center of mass you can pull in now. Applying a torque out here, and the torque is causing some angular acceleration. And I want to know, here, I'll hold him again. Is it easier to accelerate him when he's got weights out there or no weights out there? What property of him are we changing other than mass when he puts the weights out there? Or actually, if he just puts his arms out. Moment of inertia, right. So mr squared, if you increase the radius, if you put some more mass out there, he's got a larger moment of inertia. And if he has a larger moment of inertia, is that going to make it easier or harder to accelerate?
Harder.
Harder to accelerate. Okay, so let's do this again. So that was just sort of talking about angular acceleration. I'm going to make it go the other way. That'll get rid of all your dizziness. Watch out, Cassidy. So keep spinning here. So now keep them out there. Keep them out there. They're getting tired, but keep them out. He has angular momentum. His angular momentum is his moment of inertia multiplied by his radians per second. So when he keeps the same moment of inertia, or sorry, same angular momentum, but goes faster,
I'm so dizzy.
what just happened? Does anybody else want to do it? He's getting dizzy. We need a fresh person. Okay, yeah, Ethan.
Oh my gosh. It feels so quick when you pull them in.
It does. It feels faster than it looks to everybody else. Everybody else is just thinking, what's the big deal?
Feels like you're moving at a million
Okay,
miles an hour.
big moment of inertia. And I'm going to give you a sort of small omega. So his momentum is his moment of inertia times his angular velocity. And in just a second, he's going to pull in his arms, and that's going to decrease. He already did it. Decrease his moment of inertia. What happened to his angular velocity? It increased. What happened to his angular momentum? Stayed the same. So how fast you go multiplied by your moment of inertia stays the same. We'll go the other way and get rid of your dizziness. Whoa, okay. Double torque. Okay, pull them in. Put them out. Yeah, if you need to slow down. Okay. All right. Now, if he spun faster and faster and faster and faster, and we super glued these things to his hands, what would happen? What's that?
They pull them apart.
Yeah, they would go out like this. They would start to stretch him out. He would rip apart. Blood would spatter. Why did I ask that? Oh yeah. So the question is, if you're going really fast and you try to pull them in, is that easy or hard? Hard. You've got to really work to do it. And if you're doing work, I'm spoiling it. I'm spoiling it. Oh well, I'm not going to say anymore. You'll see it in a little while that I have spoiled it. Okay, so now for some calculations. Suppose an ice skater is spinning at 0.8 revolutions per second with her arms extended. She has a moment of inertia of 2.34. This is a lot bigger than the rubber band cars' moments of inertia. They're going to be like 1/10,000th of that. And that's when her arms are extended, but when she pulls them in, it drops to 0.363, much smaller moment of inertia. So we're going to do some calculations, basically putting numbers to what we just saw with Chris and Ethan. So initial angular velocity in radians per second. What number up here gives us angular velocity? Yeah, this is angular velocity. It's just not the right units. 0.8 revolutions per second. What do I multiply that by to make it radians per second? What's that? 2 pi. So I want radians, and I need to cancel out revolutions. 1 revolution is 2 pi radians. So revolutions goes away, and we get 5.03 radians per second. That's lowercase omega. So our angular momentum is L sub I, which is initial moment of inertia times initial angular speed. And her initial moment of inertia is 2.34 with the funny units that moment of inertia has, kilograms, meters squared. And that's multiplied by 5.03 radians per second. And when you multiply them together, you get really funny units, and a funny thing happens. So you get 11.8, and what would the units be? Kilograms meters squared stays. What else? Of these, which one gets to stay? Per second. The radians, poof, just gone. Because radians isn't really anything anyway. It's meters divided by meters. It's arc length divided by radius. So exactly what it is just very weird. But this is This is the unit for angular momentum. Now we have to find her final angular velocity. So we know how much angular momentum she had in the beginning. How do we get the final angular velocity? Her initial was 5.03. Is it going to be faster than that or slower than that? She's pulling in her arms. Her moment of inertia is going from big, 2.34, down to very little. So
Momentum in the new inertia.
yeah, so we use the law of conservation of angular momentum. Li equals L final. And we already calculated the initial angular momentum, 11.8 kilograms meters squared per second. And unless there's some external torque acting on her, there probably is. There's probably a little friction, but let's just ignore that. The total momentum has to still be 11.8. But we can, instead of putting 11.8 over here, which would be silly, we can put in I times omega. And the new I is given, 0.363 kilograms meters squared per, no, kilograms meters squared. And the new omega is what we're looking for. So 11.8 divided by 0.363 is 32.4 radians per second. So she went from 5.03 to 32.4. So this is around 6 revolutions per second, and that's a little less than 1 revolution per second. And now, just for kicks, because it is a worthwhile thing to do, we're going to compare her rotational kinetic energy before and after she does this. So do you remember, what is the formula for rotational kinetic energy? 1/2 I omega squared. So I just need to do 1/2 times whatever her original moment of inertia was, which is 2.34 kilograms meters squared, times her original angular speed, which is 5.03 radians per second, and the units, the number is 29.6. What would the units be? Kilograms meters squared per second. Oh wait, sorry, I left something out. Should be per second squared. This omega is supposed to be squared, so we need to square that. That gives us 29.6. But there's another name for kilograms meters squared per second squared. What are we finding? Kinetic energy. What's the units for energy? Joules. So just for kicks, I did this in the other class. It wasn't too painful. If you think back about work equals force times distance, and force equals ma. So force is newtons, and newtons is kilograms times meters per second squared. And if you take kilograms meters per second squared and you multiply it by meters to get work, which the units are joules, then you get kilograms meters squared per second squared. So a kilogram meter squared per second squared is a joule. And then for the final kinetic energy, it's going to be 1/2. I'm not going to write the formula again, but multiplied by the new moment of inertia, which is 0.363 kilograms meters squared, times the square of the new angular velocity, 32.4 radians per second squared, and that comes out to 191 joules. So she's got a lot more energy when she pulls her arms in. And why? Where does that energy come from? What? Yeah, this is what I spoiled. She's doing work. In order to pull your arms in when you're moving fast, you've got to actually exert a force. Have you been on the ride at the fair where you spin around and you get thrown into the wall? Have you tried to do a sit-up? So it's really hard. So when you do that sit-up, what's happening to the overall speed of the ride? It's increasing because you're decreasing its overall moment of inertia. So if everybody on the ride were strong enough to climb into the center, you could get that thing going really fast. It would be really dangerous. Like if you had super beings who could go on the ride and all, like, you're super dense and you all climb to the center really fast, do you think you could make the guy at the center explode? That'd be an interesting thing. So anyway, the answer to why is she does work on the system by pulling in her arms.